Hello, everybody. My name is Mark Holmes. I'm the Senior Editorial Director of Via Satellite. Today's webinar is another in a series of events that Via Satellite produces to provide additional information to our other products such as Via Satellite, Satellite News and Satellite Today. Today, we are delighted to bring you a webinar titled The Confluence of Safety and Security in Critical Systems, brought to you by Wind River. The confluence, the intersection and overlap between these two critical aspects is essential for the reliable and safe operation of the modern system, especially in automotive, aerospace, medical devices, industrial control systems, and critical infrastructure. In this webinar, we will discuss how safety critical embedded systems design teams and operation teams must begin designing from the ground up with safety and security top of mind. Our speakers today will be Monty Forehand, Director of the R&D Security Office of Wind River, and Stefan Harworth, who is a Field Application Engineer of Wind River. So without further ado, let's hand over to our first speaker. Stefan, welcome.
So welcome to our webinar. Today, Monty and I will talk about the confluence of safety and security, which is especially cybersecurity requirements in embedded systems. Or in other words, we are trying to give an answer to this question that you have seen already a couple of seconds now, which is the question, is there safety without security? So our focus is on embedded or cyber physical systems, but from across all different industries, such as automotive, industrial devices, medical, or aerospace and defense. First, we will start off with an overview on how the two terms safety and security relate and what the differences are. And this is quite important, as the two words might casually be mixed up. A couple of languages even only have one word for both concepts, like here in Germany, we always use the word Sicherheit to refer to both concepts. So from this differentiation, we will then dig deeper into each of the fields. First, Monty will give an insight into security, the latest trends, the new regulations across markets and industry, followed by safety and how that field is evolving in the light of new technological trends. In our final section, we will then give an insight into the challenges to design systems that need to be both safe and secure, and why this is becoming increasingly important. But to lay the ground, we want to start by an introduction of safety and security as concepts. So let's consider a traffic sign recognition system, which is usually a camera-based system in the car that does some hardware, software-based recognition of what is on the traffic signs, either to display it to the driver in the dashboard, as you can see here, or as input into the increasing number of self-driving capabilities within the car. Now, looking at the aspect of safety in the design of such a system, this is primarily focused on preventing any harm caused by the system to others that could come from a failure condition within the system. So as an example, the traffic sign here could be misinterpreted, and instead of 20 kilometers per hour, the car would think it could go at 50 or 60 or even 120 kilometers per hour, which would obviously be a huge danger for the passengers, pedestrians, or cyclists around the car. So a safe design needs to consider these failure conditions and ensure continued safe operation when they occur. This is achieved through exhaustive risk-based analysis to identify the conditions, which could be things like rain or fog making the sign difficult to recognize, or driving into other countries where they could have a different signage on the road signs. The rigorous design processes are then used to implement the safety measures, and extensive testing verifies that the identified risks are minimized with these safety measures. And the more critical and risky anything is, the more rigor and testing is applied on the safety measure side. Security has a different view on the system. So it's in our example, it's not about the fog or the rain causing problems. It's more about like someone spraying over the traffic sign. So if it reads 20, it would then read 120 for the car. And the same result, the car thinks it could go much faster, and with an autonomous driving capability, it would cause serious harm for sure. Now, while the effect is similar, the difference is that in this case, we have a malicious actor from the outside who is intentionally causing our system to fail. In this case, security experts then talk about protecting the assets of the system, and that security properties, such in this example, integrity or availability, are compromised by the malicious actor. A secure design is then also focused around identifying such risks. But since malicious human actors can be very creative and potentially everywhere, the scope cannot be exhaustively analyzed as we had in the safety case. So the goal is more to make the system resilient against threats and attacks that have been identified now and that could come up in the future. Now, in addition, cybersecurity is actually a true subset of security in general. And it describes the malicious attacks that are based on utilizing the hardware and software of the system, which is what we are focusing on in our webinar today. But it's also important to highlight that the security challenges around the malicious human actor and identifying those potential threats and attack scenarios is even more difficult here. Here, the attack in our example would not be to just spray an additional one or two or three traffic signs within the city, but instead to make the traffic sign recognition system itself silently add +20 or +100 to the speed limit it recognized. And this could be, like this attack could be rolled out to all cars of a certain brand that are virtually everywhere. So the potential attack vectors or scenarios could be very different for this kind of attack. They could include remote code execution by hacking from the internet via the in-vehicle infotainment Spotify app as one example, or manipulating the bus messages via code execution on a very different subsystem, or even with a malware that was already introduced during the development of the subsystem of our traffic sign recognition subsystem within the hardware software supply chain, which is, for example, possible through third-party libraries that got compromised. So cybersecurity, very much in particular, asks for the continuous reassessment and updates over the lifetime to maintain the product security of the product.
Now let's look at the trends for product security and how those are driving security imperatives and scalable and standards-based foundations for security across intelligent systems. There are many security trends that, including generative AI and post-quantum cryptography, which deserve a webinar of their own. Today, we'd like to emphasize that regulators and the community are getting or have gotten serious about security. For example, the United States Executive Order on improving the nation's cybersecurity came out in 2021. This resulted in requirements for attestation of secure software development practices. These attestations are now required for US government agencies to produce software. Not to be outdone, the European Union is finalizing the EU Cyber Resilience Act, which will also impose stringent secure development practices onto organizations and severe monetary penalties for non-compliance. With open source proliferation, we also now see a variety of groups have formed for empowerment and accountability around security and open source. And by the way, every major standard and regulation are now requiring security compliance for open source that is used in products, along with requirements for SBOMs and vulnerability transparency. With these current and emerging security trends, we see that a secure development lifecycle is now a fundamental imperative across industries, customers, and geographies, and is foundational to achieving safe products, as we will discuss in more detail later. We must consider good security development practices from the sourcing of components, including open source, as we mentioned, and throughout the development to the end of life of the product. Validating this imperative is the Executive Order 14028, which resulted in the NIST Special Publication 800-218, entitled Secure Software Development Framework, or SSDF for short. This framework defines the secure development practices that must be achieved for US government procurement of software. As of June this year, 2024, the Secure Software Development Attestation Form is now required to be submitted to CISA for authorization for use by US government agencies. Building upon the secure development foundation, there are modern functional security requirements, of which we see this special publication 800-53 as a guiding baseline. As well, 800-53 has tailored subsets across many industries and use cases. For example, 800-161, 800-171, and FedRAMP, along with mapping to most US security frameworks. Today's world demands that the software that is running and the data are trusted in both content and integrity, and that the customer can verify those with integrity checks and SBOMs. These are realized with a number of features that are rooted in the secure development lifecycle process. These secure capabilities then become the scalable foundation for integration across numerous compute, storage, and network platforms and industries for security by design across the digital experience. As with any discussion on standards, I try to remember that there are 5 to 6 digits after ISO and 6 digits after NIST. So there's a lot of standards for sure. So we need to create and must create scale and leverage in our approaches if we are to span the standards landscape with solutions that the world can afford. Building upon that, we see that security and trust start with a standards-based foundation that spans a secure enterprise environment, secure products, and secure development. This empowers security scaling and broad-based security compliance across many industry standards and regulations, spanning A&D, industrial, automotive, telecom, finance, medical, and more, and across many geographies and regulatory environments. As well, our experience shows that there is a complementary approach and overlap amongst many of the safety standards, such as DO 178, ISO 26262, 61508, and others. Summing it up, with a standards-based approach, we can empower a security and trust foundation for secure and safe intelligent systems.
And as Monty just pointed out for the security side, and he already mentioned some of the safety standards, so there's also a huge foundation of safety standards and a well-established landscape. And to give you a bit of an insight into this, so here you can see the different industry standards, and most of the standards are really specific and unique for each industry. This seems at first like a major obstacle to have overlap and synergies between them. But fortunately, all the standards share a set of common goals, and this is to identify and assess the safety risks, to set up measures to handle or mitigate them, and to verify the functionality of these safety measures. Even more, the standards are actually very similar in the requirements for a safe development lifecycle, as well as for the level and rigorousness of the documentation. So while every standard has some kind of special sauce, the majority of the documentation is actually equivalent, which enables a mapping or reuse between the different standards once you have one complete set of documentation for one of them. Many of the standards you can see on this slide are actually derivatives of the more generic IEC 61508 on the left-hand side. And they cater to the specifics for the different industries, like ISO 26262 for the automotive industry. The major exception here is the space and aerospace industries, which also tend to have separate standards for the system level, the software, and hardware, which is the reason for the footnote related to the aerospace standard on this slide. Now, in general, the safety development processes usually are all a unidirectional flow that ultimately leads to a certification of the system. And this is then followed by a post-deployment or in-service management phase. The start of the definition is a scope definition. The start of the development is a scope definition, and exhaustive analysis of the potential safety hazards, as we mentioned before. From there, the specification and formal requirements are developed and refined into a design and an implementation, both for software and hardware. This refinement process usually looks much like the letter V, where the levels of refinement down on the left-hand side are followed by going back upstairs with the different testing and integration levels on the right-hand side. Every integration step fully verifies the implementation against the corresponding level of requirements. And since every item on every level on both the left and the right-hand side of the V also has a reference to the next higher or lower level, a full traceability between all the items created along the safety development cycle is achieved. What this means is that on the highest safety levels, every single line of code in the implementation of the software can be traced back to a system level requirement and to the different tests that verified its function on different levels. The safety development process ultimately leads to a formal certification or accreditation or approval of the system, which can be very different depending on what industry we're talking about. So as an example, a national aviation authority like the EASA or the FAA will approve the aircraft software by actually auditing the complete documentation evidence developed during this V cycle. And this is done for all the subsystems before the aircraft can take off. That's very different to what happens with cars or in many other industrial systems, where the type approval or the approval to put the system on the market does not include a full audit of the software by some, let's say, government agency. Instead, in these industries, the suppliers will have their safety documentation approved by a private company like the TÜV in Germany and use the TÜV certificate to demonstrate that they followed state-of-the-art safety practices, which is in the end used to limit the liability in case something happens, even though they used all the measures to develop a safe system. So when developing a safety critical system, it is really important to have partners that understand these very basic differences of the different industries to ensure a successful project. As said before, a commonality to all safety standards is the assessment and classification of safety risks, which means the potential harm that the system could cause to the outside world. Now, of course, it would be impractical to classify a whole car or a piece of machinery only based on the most likely or most hazardous safety risks. So before the classification happens, the system is actually decomposed into subsystems or functions. The different safety standards then have their own names for the different categories of safety criticality or integrity levels. And while the categories are often compared similar to what you can see here on the slide, there are actual differences in how the standards approach this classification. So whether it is by mathematically calculating the risk of failure for the system, which is the case in the IEC 61508, or by focusing more on qualitative categories like catastrophic or major failure, like for the ISO or for the DO 178C. However, in all cases, the goal is always to reduce the identified risk for a function to an acceptable level. And this could, for example, mean that in the end you have to demonstrate that your system will not fail more often than whatever, once every 100 million hours of operation for this particular hazard. The safety classification of the function then also defines the rigor applied in the development process. So for low integrity levels like the ZIL1 or DAL-D on this slide, only a high-level formal description and high-level tests of the software are required. Whereas for DAL-A, as an example, as the highest aerospace integrity level, every single line of assembly code in the final software binaries must be fully documented and traced completely within the evidence documentation, which means back to system level requirements and back to system level tests. It should not come as a surprise that the price of developing software rises dramatically for high integrity levels with these kind of requirements. Even more so, the rigorous requirements for the documentation make it extremely difficult to change the software after the certification is completed, as everything in the evidence needs to be revisited and reviewed even upon the slightest change of the software. Therefore, when new hazards from a safety perspective are uncovered after the system has been delivered to customers, a change to the software code or the hardware design is often the least preferred way to mitigate these new hazards, and you're more looking into like operational ways to work around them. Consolidation approaches in the implementation can help to bring different functions and even with different criticality levels back onto a single piece of hardware, so to reduce the complexity of the overall system. By using the right tools and processes, it is possible to even have functions with different safety classifications run side by side on the same CPU or processor. The aerospace industry has been leading in this direction for several years, and the concepts of this so-called integrated modular avionics can be leveraged for other industries and standards as well. This can enable even incremental certification, which is a process that allows to later replace or update individual functions in a consolidated system without a complete recertification of the whole system, but instead you just need to revalidate the replaced items or functions. Now, on a more technical level, unlike the security standards like NIST 853 that Monty discussed before, the safety standards usually mandate the goal of risk reduction, as I explained, but they do not really prescribe how to get there and what features or techniques like the ones here on this slide you could use for that. On the other hand, there are supportive application framework standards. So examples include the ARINC 653 for avionics or adaptive autodesign in the automotive industry, which provide technical and architectural considerations and restrictions to the application developers. However, following these standards alone is not sufficient to achieve safety certification, so there is kind of a gap between. A variety of techniques like here on the slide are used when you implement safety critical software. And many of these include the use of hardware features that you find in modern processors. So examples here are redundancy, where you could use dual core lockstep in smaller microcontrollers, or to implement isolation and partitioning, the use of memory management units or I/O management units in modern processors, together with the help of hypervisors and real-time operating systems, is also a common technique to achieve safety software design. But also security-focused features such as event monitoring units or the trusted execution environment that Monty had on his slide can be helpful to support safety software development. What our safety experts at Wind River see and hear in the market are multiple trends that challenge the usual safety development process as I described it before. This can be because the scope becomes unclearer for the system, as with artificial intelligence systems and autonomous decisions taken by the systems. Or because the pace of the evolving technologies that produce simply too much input for the traditional safety processes. So examples for this are the challenges around interferences in modern multi-core processors, but also the question how you can leverage cutting-edge innovation that is usually happening in open source software these days, and how to transfer that into safety system development. Now, the open source software topic will even have a dedicated critical software track as part of this year's Open Source Summit in Vienna next week, where you can hear our safety expert Olivier Charrier speaking, just in case you're heading for Vienna. Our focus today, though, is on the combination of formal safety and formal security, which is also one of the trends that is challenging safety development processes as are commonly known. But also the trend here is that this is becoming more mandatory for future systems. So let's have a look what this means in detail and what are the driving factors for that. Now, bringing back our initial example as a background, the basic security threats that I outlined in this initial example at the beginning, they have already existed for a while, but they are becoming more and more critical with more connected and autonomous systems, not just in automotive, but across all industries, basically. Also, what we see is that the attack vectors themselves are continuously becoming more sophisticated. We had Spectre a few years ago. We had this very sophisticated XSET backdoor attack against OpenSSH earlier this year, in case you noticed it. And what is common to these threats is that they also can affect already deployed safety systems in the field as well. At the same time, the regulation for cybersecurity in the context of safety critical systems is becoming reality. As an example, aerospace, the EASA in Europe has already added cybersecurity measures as a requirement, and they have accepted the D03XX and ED20X standard series as an acceptable means of compliance for that. And FAA in the US is currently in the process of aligning to that. But also in the automotive sector, recently the adoption of a new European law showed a direct business impact to one of the vendors. Porsche had actually to stop selling some of their models prematurely, simply because retrofitting cybersecurity into their processes and into their products was too costly in that case. So even for industries where there is no safety and security regulation yet, ignoring this trend can have a serious impact on the business sooner or later. So, but when it comes to actually bringing together the safety and security in a system design, it is important to keep in mind that the two must be kept separate from a system point of view. Because as we have seen earlier, the safety and security life cycles, while they share a lot of similarities, so examples, the processes and requirements on the organizations for the two go well together. You have comprehensive documentation in both cases, the technical features overlap. Actually, both fields can somewhat benefit from each other. So if you have the small and thoroughly tested code base in a high criticality safety system, this naturally provides a smaller attack surface from a security point of view. Or the robustness and resilience of secure systems is what is supporting safety considerations as well. But it is important to be aware that the way the two fields are actually very different in how they look at the system, in the way they look at the system. And this has a very large impact on how the scope definition and the risk assessment actually works. So all the way down to the software level, this actually translates into a couple of challenges. And in particular, I have picked out the different velocities here around maintaining safety and security systems over their life cycle. So while security, and in particular cybersecurity, as we said initially, requires to be constantly on the watch and react to new threats and attack scenarios with updates to the existing security measures, the safety process, on the other hand, is trying to avoid software changes, usually at all cost, due to the huge effort of recertification. Fortunately, as we keep safety and security independent in our look at the system level, we can also realize that a high safety integrity does not necessarily always mean a high security assurance. So bring back our car as an example. The airbag control unit is obviously a very safety critical system, and failure can lead to a serious harm of passengers. At the same time, this unit is usually deeply embedded within the car and only has very few connections to other subsystems. That means it has few potential attack vectors from a security point of view and might end up with a low security assurance in your analysis of the system. On the other end of the spectrum, the powerful in-vehicle infotainment system has a large attack surface, with internet connectivity and complex applications sometimes coming from third-party suppliers, like take Spotify, Apple, Android, whatever. Yet, it might be designed in a way that it only has a low safety integrity level because it is not directly related to the safety functionality of the car. Now, the greatest challenge for the confluence of security and safety is actually for those subsystems where the high safety and the high security assurance comes together. And this unfortunately affects the increasing number of autonomous driving subsystems in the car or similar autonomous functions in other products. And the commonalities are here that these systems usually require extensive sensor data. They also rely on up-to-date external information. So in the car, for example, road and traffic updates. And they also have complex application stacks to process and display the data and take the autonomous decisions, while at the same time, obviously, being very critical to the safety of the overall system. As a side note, I put the tire pressure monitoring system as a low safety security example. And just today I read that there's a sophisticated attack on Tesla cars where they used the TPMS and somehow got into the got a remote code execution on some immobility issue. So it's not as easy as the examples are sometimes. As I said, addressing the challenge of combined high security and high safety systems is certainly the most difficult part. But as a software company with broad expertise in both areas of safety and security, we at Wind River see a number of different approaches that can help to tackle this problem. So first of all, a number of techniques that we already touched in both the security and safety sections can be very helpful here. The idea of partitioning and isolation is even more important for the safety and security confluence. Modern processor designs provide both hardware and software approaches for that. So for hardware features, we have, for example, the trusted execution environments or the safety islands on modern system on chip, where a second set of CPU cores is combined with hardware-based safety assurance, such as lock stepping and monitoring units. However, we think that relying only on hardware protection can be problematic, in particular from a security point of view. Since when vulnerabilities are uncovered later, and let's bring back Spectre as the example, it is virtually impossible to upgrade the hardware in your millions of cars or in satellites that are already up in the orbit. And this is where actually the use of software-based technologies can have an edge. So by using safety certifiable hypervisors like our Wind River Helix virtualization platform, or other concepts like containers in Linux and real-time OSs, you can have an advantage in approaching this. Beyond that, the concepts of such as layered defense, where you combine a security hardened Linux that shields a safety OS or a subsystem and moves them into a different category in the security analysis. So to make the system more positioned like the airbag control unit that we had in the previous slide. Also, the use of modern memory-safe languages like Rust can actually help to reduce the verification efforts. And they might remove a whole class of potential attack vectors altogether, which are through the memory bugs in the software. So another piece of advanced technology that can help to address challenges on both ends. If we look on a higher level, we also see again that safety and security can in some ways both help and strengthen each other. First, the use of pre-validated and off-the-shelf building blocks for safety software that come with a off-the-shelf certification evidence to the highest criticality levels can also be a great asset from a security point of view. Not only is the code base small, well-defined, and extensively tested through the safety processes and has a small attack surface, but by basing it on a secure development lifecycle, the security considerations and practices already flow into the software design and implementation of the safe building block here. On the other hand, accelerating safety development processes creates the ability to react to new security threats as they come up and even after the system has undergone safety certification. This obviously requires to have fast revalidation of existing safety system software, which can be achieved by adopting CI/CD methodologies and leveraging the processing power of cloud infrastructures for development and testing. This is what we can provide with our new Wind River Studio product. In the combination with the benefits of consolidated systems and incremental certification, as we discussed before, the goal can even be to reach something that is called a continuous certification process, which is a way to keep a system resilient from a security point of view over the life cycle while still retaining the safety measures and safety properties of the system. So why is Wind River the right partner on this journey to bring safety and security together in the systems? For our customers, the appropriate certification of their safety critical systems is a market differentiator. And in some industries, like in aerospace, it is legally mandatory. However, the process itself is cumbersome, it's time consuming, and it's very resource intensive. So having a partner that has a deep understanding and expertise for security and safety and for the specific industries and markets is critical here. For us as Wind River to offer this, it begins internally with how we develop our own platforms for the intelligent edge. We have VxWorks, Wind River Linux, Helix virtualization platform as examples. Our internal product development processes incorporate industry recognized software frameworks and development standards such as POSIX, FACE, RING653, Linux Standard Base, and others, so that we ensure the architecture meets the industry standards in areas such as portability, interoperability, efficiency, and high-performance processing. On top, our processes utilize cybersecurity methods across the board, and the Wind River Secure Development Lifecycle aligns with the NIST standards and their principles, as Monty elaborated earlier. We also create full off-the-shelf certification evidence for our VxWorks and Helix virtualization platform products, and TÜV certificates for standards such as IEC 61508, where this is applicable. This makes us an approved vendor across multiple industry sectors. And in addition to the warranties that we give on our certification evidence material, we also support and aid customers in the form of workshops, mentoring, and project-specific add-ons to the products with the experts in our professional services teams. So to help reduce the time to market and the risk in your safety certification projects. And last but not least, by leveraging our cloud-native development platform, Wind River Studio, we lay the foundation for safe and secure continuous development, integration, and certification. And on top of all of this, our security center provides the vulnerability alerts, the constantly up-to-date CVE vulnerability analyses, and patches where applicable, all backed by an incident response team. So please feel free to reach out to us if you're interested in more details, and our local teams will be happy to help you. And with that, I would like to say thank you and hand back over to Mark for the Q&A.
Okay, thank you. So a big thank you to Stefan and a big thank you to Monty. That was a really interesting, thought-provoking presentation. We are now entering the Q&A part of the webinar. We have a question here regarding Wind River certification, and traditional Wind River certification was focused on DO 178, ARINC 653 with new ownership. Will there be more of a focus on ISO 26262? So,
I can take that one. Indeed, many of our products, or most of our products, have seen certification to DO 178C, so to aerospace standards. But over the past 2 decades, we have also produced a number of certification evidence packages for other standards, such as IEC 61508. Now, with the increasing demand for safety and formal safety certification in the automotive market, it is clear that for us, ISO 26262 is becoming a relevant asset to provide along with our products. Now, certainly being owned by Aptiv now in the second year is something that is helping on that journey. But indeed, even without that, I think adopting automotive safety certification is something that we are very much looking at. And in fact, we have added that to our portfolio for the Helix virtualization platform as an example.
Okay, let me go on to the second question. And as I said, if you want to submit a question, go to the right-hand side and submit your questions. We have a question about, are embedded hypervisors becoming a must-have in modern embedded systems from a safety point of view?
I will take that one as well, as it's a very safety-related question. So I would say the basic answer, whether they are a must-have, the basic answer is no. It really always depends on the use cases, and since one of the goals of safety system design is to have in the system only what you need, and to have, like, for every piece of software you want to have requirements, at least for the higher safety integrity levels. It's usually not really the goal to use a hypervisor just because it is there. However, there are still a couple of good reasons why you might want to use an embedded hypervisor. So the first and very obvious one is when you look into consolidated systems where you have multiple safety functions, or where you want to kind of have this layering between safety, like I sketched out before with a security hardened Linux and a safety RTOS, and you could consolidate that into one piece of hardware. So that might be one use case for the hypervisor. Another actual use case, which is not that obvious for embedded hypervisors in the safety space, is that even if you just have one function in the system, the hypervisor can provide a very good safety net around what you would regularly develop as part of, or with a single operating system kernel. So since the hypervisor is leveraging a completely another set of hardware protection features, such as the IOMMU as an example in the processor, it can bring additional benefit when it comes to fault isolation and fault containment in your system, and thereby fail-safe operation in case you have a problem with the system. So I would say there are a lot of benefits for embedded hypervisors in safety systems, but it's not a must-have. And in fact, with our VxWorks Cert, for example, you also have a product where you can develop, in most cases, it's addressing single level of safety criticality, but with the use of user space processes, you can even achieve multiple level of safety in some of the markets, depending on the safety certification. And that is without a hypervisor.
Okay, let me go on to another question. And again, if you want to ask a question, there is a question tab on the right-hand side, so please feel free to submit your questions. Do you feel like an IMA approach for safety certification purposes helps or detracts from security requirements, especially for data at rest or exposures when powered down?
So an IMA, or integrated modular avionics approach for safety certification, is very much related to this idea of consolidation and bringing together multiple safety functions on a single piece of hardware. The IMA or the standard that is usually used on the technical level to describe IMA systems is the RN 653 standard, and it does not really mandate an implementation of the OS, but in what we at Wind River think is the best way to implement an IMA platform is to leverage a hypervisor from the technical end. So by using this, whether this approach helps or detracts from security requirements, I think it's more helpful actually. In the cases where the integrated modular avionics platform is implemented using a hypervisor in particular. And the reason is that these hypervisor-based designs for IMA platforms share a lot of the properties that you might know from separation kernel concepts that are coming from the common criteria in the security world. And by having the hypervisor and the separate individual operating system kernels for each of the different partitions, as it is called in the IMA approach, you have a clear separation of concerns, and it is easier to demonstrate also that you achieve certain security requirements or properties. Now, in the question, the data at rest or exposures when powered down were mentioned. I think these are probably the least interesting parts, maybe when it comes to the IMA approach and the use of hypervisors, as I just sketched out, because data at rest or exposures when powered down, for me, really point to things like data encryption or trusted boot, which is really outside the scope of the IMA platform. So this is maybe an aspect related to the safety and security confluence as well, that what we already see in aerospace systems that also might have like national security requirements because they go into military systems, is that, for example, data at rest protection is more handled, just like trusted boot, as I sketched out, are more handled in a stage before the IMA platform actually starts. So you have kind of like the initialization phase of the system, where you start to decrypt the data and where you ensure with a trusted boot that the integrity of the software is as expected. And only then you switch over, let's say, to the safety operational mode, where really the IMA approach kicks in. But in summary, I think an IMA approach can be rather helpful to fulfill security requirements if the IMA platform has a kind of a beneficial architecture to support security.
Okay. I have a question regarding software delivery mechanisms, and what software delivery mechanisms are effective to update security features without disturbing safety certified components. So who wants to take that
So I guess I'll go ahead and take that one.
Sure, go ahead.
Yeah, and then I'll let Stefan add on as needed. So I think the techniques that Stefan talked to about the confluence of safety and security become increasingly important as we move forward. So, you heard the words continuous integration, continuous deployment, but you also heard the words continuous certification. And I think that's really part of the message today, is bringing those three concepts together and actually doing them, creates the environment where these two things come much closer together. And I think those are the techniques that that we're going to need to do as a world moving forward to bring those two things together and not disrupt each other. And Stefan mentioned velocity, and I think bring those two velocities together and much closer together as we move forward. Stefan, you have anything to add to that?
Maybe just the pointer back to the previous answer that I gave with this IMA and data at rest, I think is also kind of applicable here. So the updating the security features without disturbing the safety certified components in the target system will usually happen like outside the operational scope of the safety software. So just like the trusted boot. But the core challenge here is really, as you pointed out, Monty, the whole bringing together of the two processes and having the velocity that you need to update security features come together with your safety development process, so that you can quickly release new versions of the safety software that have the updated security features in them.
Okay, just a quick reminder, we have just around 10 minutes left, so if you have questions, submit them sooner rather than later so we can get them in. As you know, you can submit them via the tab on the right hand side, so get those questions coming in and we'll get them in hopefully in the last few minutes. A question like, if I'm not in government, can I see a company's secure software development attestation form, and are they publicly available? So who wants to take that one?
Yeah, I'll take that. Yeah. So I think the references to the secure software development attestation form, and so for us, we provide those number one to the government through the CISA portal, but secondarily we provide a attestation form that's available to our customers under non-disclosure agreement. So two paths there. So I think the answer is yes. If you're a NDA level customer with us, you can get attestation form of secure development.
Okay, let's go on to the questions that are coming.
Thanks for noticing that, whoever asked that question. Yeah, thanks for doing your homework.
No problems. These are great questions, and keep them coming. We're really enjoying this discussion. Question now, can you elaborate how Wind River aims to address mixed criticality environment in environments where advanced techniques like TEE is not possible, costly, and how a software approach can be used? Interesting question, that one. Who wants to, Stefan or Monty, which one of you want to take this one?
Yeah, I can take it. So I just assume that TEE is referring once again to the trusted execution environment, and that we also mentioned during the presentation. So yeah, addressing mixed criticality environment or mixed criticality systems in environments where advanced techniques are not available is, let's say, kind of the caveat with the hypervisor-based IMA designs that I just outlined, and where I argued that they have a couple of advantages also when it comes to safety and security. Now, the issue is that using a hypervisor also requires certain prerequisites in the hardware platform. So modern application processors like recent Intel platforms, Intel Tiger Lake as an example for a safety certifiable hardware processor architecture, or the Cortex-A family from ARM, which is very popular, obviously, in the embedded market. Now, these processors usually have all the prerequisites that you need to have a hypervisor that is as powerful that it can provide mixed criticality environments for an IMA system, as an example. Now, if you're looking at processors that do not come with these features or technologies, and from my experience, usually this refers to architectures like the Cortex-M series or the Cortex-R series, which are more going into the direction of microcontroller architectures. These processor architectures sometimes have features that relate to virtualization. They also have protection features to separate memory between different applications. But all of this on a very basic level and in very static fashion, most of all. So they usually only have like 32 different memory regions, whereas a powerful application processor has a freely configurable memory management unit, which allows you to define arbitrary memory regions and protect them from each other. So the answer is that, as I outlined before, we have our monolithic VxWorks based certification systems that are primarily addressing single level of criticality, but with the use of user mode processes also enable mixed criticality for some standards, but not for all. Like, it's not working as good in the aerospace industry with this approach. So these, this architecture is also usable on lower end processors and processors that do not come with advanced technologies like the trusted execution environment or hypervisor hardware-based virtualization capabilities. But usually it will come with some restrictions. So looking at the more powerful application-based processors with all the hardware virtualization capabilities, this is something that I would rather recommend if you're looking into mixed criticality environments, unless you're okay to have a couple of really strenuous restrictions on your development.
Okay, fantastic. I'll just do a final call for questions because we're getting towards the end of the webinar. If you've got any questions, please submit them on the question tab on the right hand side, and we'll see if we can get them in. But we do have a couple more here. So we have a question: how does the concepts you show today oh, sorry, not that one. That's the wrong one. The great discussion today, someone has just said, to support continuous certification, are there aspects of the V process that can be easily automated?
So I'll pipe in here and then let Stefan build upon that. But I mean, the answer is yes. And if you're really truly going to talk about continuous integration, continuous deployment, or continuous certification, the next words in that sentence have to be automation, right? So I think there are places where that can be automated, and we should all be looking for the places where it all can be automated, or nearly all of it, given the challenge in front of us and the continuous integration that we need to do to be successful here. I'll let Stefan add on there if he chooses.
Yeah, I think the parts of the V process that can be that are like most attractive for automation are obviously the different stages of test, which usually make up more than 50% of the overall effort. But obviously also the whole complex of traceability and ensuring that everything is connected with everything, and validating that is also something that can benefit a lot from automation, obviously.
I would like to say a big thank you to Monty and Stefan. Really great presentation, and really enjoyed that. And I also want to thank our audience for taking part as well. For those who watched and who asked questions, lots of great questions came in. We really appreciate that, and it's been great working with Wind River also. So the Via Satellite webinar series will return soon, and we look forward to seeing you there. So just one final big thanks to Stefan and Monty, and we look forward to seeing you all again very soon. So thank you very much for your time today.